Welcome back to Lehigh Tutoring. So, what I got a question from someone on Instagram, so I figured I would answer it before continuing on to the actual material. So basically, the question that he asked was, what is the cross-sectional area of a sphere with a diameter 1 meter? Well, first of all, if you've got a sphere with a diameter of 1, right, that means that the radius is going to be 0.5 meters. So keep that in mind. So the radius numerically is going to be 0.5 if we're considering units of meters. And what cross-sectional area essentially means is what you're doing is as long as you create a coordinate system, in this case it's a right-handed coordinate system, and you have the sphere centered at 0, 0, 0, what you can do is you can cut the sphere into these slices. Okay, and I'm even going to get one in the center. And by the center, I mean centered about 0, 0, 0. And I did a poor drawing here in terms of these cross-sectional areas, but they're supposed to be circles. And these circles, those areas of these circles that I've cut out is what you're looking for. And it's obviously going to be variable. It's going to change. So we need to figure out how it changes. Well, if you look closely, right, each radius, okay, is actually the z coordinate. Each one, right? Z is the one that's changing. Z is the variable that's causing the change in the radius. So what you can do is just simply write pi z squared. Okay, but if we're talking about a sphere, we're talking about spherical polar coordinates, and what that means is that you've got z in spherical polar coordinates is r times cosine of phi, and what phi is the angle, right? Remember, it's centered. So if I'm looking at this cross-sectional area for this guy, right, phi is the angle from the zero axis, from the origin, sorry, excuse me, it's from the z-axis all the way to the point of interest. So that's phi. So if I just plug this in, I get pi r squared cosine squared phi, okay? And r again was 0.5, that's 1 over 2. You square that, you get 1 over 4. So you get pi over 4 cosine squared phi. So that would be the cross-sectional area of a sphere with diameter 1 meter. Alternatively, you could cut it this way as well. Okay, and then, oops. And in that case, you'd get variable y, right? And then you could also have done it a different way, variable y and variable x as well. Yeah, so that is the question. Hopefully that answers the gentleman's question on Instagram, or the person's question on Instagram. Okay, so continuing on, in the first episode, I introduced the concept of the wave function, and the wave function was psi. I should have used an uppercase psi, but I didn't. It's okay. And the psi was dependent on x and t, and psi is supposed to represent a state of a particle. And so one thing that came up was that, you know, whenever we're talking about classical mechanics, we're trying to draw analogs between quantum mechanics and classical mechanics to make sense of what we're doing here. In classical mechanics, you would figure out a particle's position as a function of time, and then from that you could get the velocity, and then from the velocity you can get the kinetic energy, and from that you've got pretty much most of the information necessary. You can find other quantities as well. In quantum mechanics, at the quantum level, you are not as certain of the particle's position. It becomes more of a statistical problem, and so you get Bourne's statistical interpretation. So you get you can find the probability of a particle being between A and B at a given point in time, and that was defined as the area under the curve of psi squared, or the absolute value of psi squared, and that's this little integral. And so the question was, okay, if you take a measurement and you find the particle to be at position C, what's happened like before taking that measurement? And there were three schools of thought. One was realist, which is to say that it was always at C, which hinted, if you go back to my previous video, you'll see that I'm talking about how that implies that quantum mechanics is an incomplete theory, because quantum mechanics says that, at best you can know in what interval it could be with some given probability, but not the precise position. The orthodox position that is still mentioned in classes today is the fact that the wave function, as soon as you take the measurement, the wave function collapses to a delta at the measurement value that you retrieved. So if you retrieved the value to be C, then it will collapse at C. And if you take a second measurement fast enough, then it would stay at C. It would be C at the second point of measurement. The agnostic position is that you don't know. I won't go into detail with that, but yeah, so episode 2 is going to be going so if we're basically talking about quantities on the quantum level from a statistical nature, then we have to talk about probability. We have to introduce probability. So best way to introduce probability, because what we're going to do is we're going to talk about continuous variables, but before that we're going to talk about discrete variables to introduce some concepts. So the Griffiths book, and I showed this in the first video, the Griffiths book, the second edition that I had a great example, and might as well just use. So if you have one person, if you have a room that has 14 people, okay, and the ages of these people, there's one person at 14, okay, there's another person at 15, there are 3 people at 16, and you have 2 people at 22, so 2 people, and you have 2 people at 24, and you have 5 people, 5 at 25. Then you might ask the question, what's the probability of picking someone at random that's 14? So at the age of 14. Well, the number of elements at age 14 is 1, right? It's just this guy, okay? And the total number of elements, n, equals 14. There were 14 people. And so what that means is the probability of drawing 14 is n over 14 divided by n, which is 1 out of 14. Okay, and you can do this with, the probability of drawing the age of 25. That would be 5 over 14. So in general, right, the probability of drawing a certain age, let's say j, is the number of elements at j divided by the total number of elements in the sample that you're considering. Okay, so what if I ask now, what is the average age of this sample that I've demonstrated here? Well, the average age is going to be essentially the following formula. And I'm gonna symbolize the average age by putting these little brackets here. So that's the average age j. The formula is essentially, if you add up all of your elements, and by all I mean if you keep adding until you're done, then it's going to be the age that you're considering times the probability of getting that age. Okay, so in this example, the average age, I can calculate it as such. So 1 over 14, okay, is so in this case I've got a total of 14, right? So that's 1 over n, that's 1 over 14. And then I just got to sum the age and the number of people at that age. Okay, so in that case, it would just be 14 by 1 plus 15 by 1 plus 3 or 16 by 3, because there are 3 people at 16, and 22 by 2, and you keep going, 24 by 2, and 25 by 5. And once you work this all out, you get an average age of, what was the average age? 21. Okay. Now notice the average age isn't actually in the sample. There's no one in that sample. It's the average of 21. But that is the average of this sample, the average age. What you call this quantity here, in quantum mechanics from now on, we're going to call it the expectation value. And it's a little confusing because it suggests that if you randomly took someone out from that age, you would get that value. So if you randomly picked a person in the group, you would expect the age to be 21, but that's not what it means. It was just it's an unfortunate term, but it's actually the expectation value, which is this guy, is just the expectation value, which is just the average. Now that's the average of the age, right? But for fun, what if we were like, what's the average of the age squared? Well, you can determine that, right? And it's this symbol, okay? And you do the same thing, except it's going to be the age squared times the probability of getting that age. Well, technically, it's going to be the probability of getting that age squared, but the probability of getting that age squared and the probability of getting that age is actually the same in this sample, right? Because if you have 14, the age squared will be 14 squared, and the probability of getting that is 1 over 14 still, right? So that is the formula for j squared. Now, what if I played around and I just had some random function? It could be like j cubed, square root of j, whatever. Then what I would do is I would just put f of j, just to basically generalize. Okay, so in general, that would be the average of the function f of j. Let me actually go back just to make sure that I'm gonna send you guys these notes once it's all said and done. Okay, so I'm there, and so moving on. So let's draw two distributions. So we've got the average pretty much down pat. Okay. Now, let's say I have on the y-axis the number of elements. Okay. And on the x-axis, I've got just some independent variable. It's kind of like a frequency distribution, pretty much, actually. If I have an average value of 10 and an average value of 10, and I draw these two peaks, watch this. So I draw these two peaks. So one is very sharp, okay, and that's very suggestive. Okay, so I've got one peak that's very sharp and another that is not, right? Then I've got two plots, two curves, where the mode is at 10 for both curves. I've got the average and the median to be at 10, but they're different plots. They don't have the same spread. Okay, they do not have the same spread. One has more spread, the one on the right has more spread than the other. So we need, before kind of taking this into a continuous, into continuous terms, from discrete to continuous, we have to find a way to measure the spread. And the way to do that is the standard deviation. Okay, now to get there, what we have to do is write down what a deviation is. So a deviation of some variable j, before it was the age, but some variable j, is by definition that value minus the average value, right? So before we had the average age being 21, right? So the deviation away from the mean for 14 is 14 minus 21. That's -7. That's -7. Okay. Now, what you can do is you can average out all these deviations, but the problem is, if you average out all the deviations to get a standard deviation, that would be 0. Okay, so what we do instead is we actually square this term. Okay, so we square this term, and then we take the average of the square. What the squaring does is it essentially it gets rid of that negative, because the reason why the average deviation is 0 is because there's an equal number on the negative side as on the positive by virtue of the fact that you're dealing with an average. So what you have to do is you have to square, and so you get the average of the square of these deviations, and then you proceed to square root that. Then you proceed to square root that, and what that leads to is the standard deviation. So what that means is if you square that, you get the variance. Another nice way to write it out is the following. Sigma equals the square root of j squared minus the average of j squared. So to get the standard deviation in our problems, all you have to do is take the average of j squared, before it was the age squared, minus the square of the average of the age, square root that, and you got this nice quantity that measures spread. Now, how does this go to continuous variables? So to get to continuous variables, if you were to deal with a continuous variable, if you were to, I guess, pick someone off the street and say, what is the probability that this person's age is between 22 years, 10 months, 16 days, 42.33333 seconds? The probability would be 0. So because there's so many options, there's an infinite number of options. Instead, what you do is you say, what is the probability that your age will be between interval 1 and, point 1 and point 2? So between age 16 and 17, maybe. That would be a finite quantity that you can measure. So so what you do is you form this probability distribution instead. And the probability distribution is rho of x, and that is the probability. So this is the probability, okay, that the individual will be between x and x plus dx, and dx is this infinitesimal distance, infinitesimal element. So what that means is that the probability to be between a and b is going to be the integral from a to b of rho x dx. Okay. So what I want to do is take the quantities that we got in the discrete variables and put them in these continuous terms. So before, if you add up all the individual probabilities of that age, um, of the age example that I showed, the probability would be 1, right? So there's 100% chance you're going to get someone at a certain age. Um, but in this case, how do we get that with continuous variables? Instead of a summation, what you do is you integrate between negative infinity and positive infinity of this probability distribution function. And what you're essentially saying is the probability of being somewhere between negative infinity for x and positive infinity has to be 1. And the average of a certain variable of interest is similar to that, j, p of j. It's very similar to that, except now it's going to be x rho of x dx. And that is the average between negative infinity to positive infinity. And then here, I can generalize that to f of x and just go, negative infinity to positive infinity, f of x rho of x dx. And then what that means is if I wanted the standard deviation, remember the standard deviation before in discrete variables was these, no, that was the variance, sorry. So I'm writing down the variance. The variance is going to be the average of j squared minus the average of j squared. So now all I have to do to put in continuous terms is our variable of interest is x, so all we have to do is replace it with x. And so to get the standard deviation, you just square root your result. Now, how does this relate to the first episode, right? Where we had psi. And I'm going to show it to you again. I wish I could jump to pages. Probably a way to do it. But so how does this relate? Well, it's this term right here. When we had the probability, this is born statistical interpretation. So the probability that a particle would be between state A and state B, or position A to position B, is going to be the integral from A to B of psi squared dx. That psi squared right here is rho of x. So if you're comparing episode 1 to 2, psi squared, right, psi squared is equal to the rho of x that we're talking about. Okay, and notice this guy, right, has time involved. So it's what you're essentially doing is you're finding the probability that a particle will be at between position A and B at a given time t. What we're also going to do later on is we're going to talk about time-independent Schrodinger equation. And so that'll give us a wave function that's time-independent as a way to simplify the problem. And then we'll move forward. What I'm going to do, so that's the end of episode 2. What I'm going to do is I'm going to post answers to this section. I hope this was informative. If not, just leave a comment and see how I can improve it. And maybe I'll do a second post or like a second video to better explain what I've talked about here. And I guess I'll just call it episode 2B or something like that. So just let me know. Subscribe, like, comment. Give me some feedback so I can figure out ways to improve the video quality. And thank you so much. Peace out.